Okay, so what are we talking about? We're now in the sort of the new part of the course, in a sense, talking about things that you haven't really heard probably almost anywhere before, and it has to do with modeling strategy, which basically has to do with, can you hear me, by the way? Can you hear me okay? Okay. And it has to do with how you work with a data analysis problem where you're doing an epidemiologic study and you have a large set of data or even a medium-sized set of data, and you have a lot of variables, and you've decided that, well, maybe I'd like to do some simple analysis like a crude analysis or a stratified analysis, but I got too many variables and to try to do that. It's too complicated, and I want to use some kind of mathematical modeling procedure. And the one we're learning about now is logistic regression. So what we're going to do is talk about, well, how do you use logistic regression and try to work with this complicated situation where you've got all these variables and you want to somehow figure out an answer to your question, which is usually an etiologic question about the relationship between an exposure and disease, and it usually has epidemiology component to a part of it where you want to make sure that you consider the kinds of things you worry about when you're doing an epidemiologic study, like confounding and interaction and precision. How do you work that in? So that's what we're talking about, okay? And what I did at the end of last time, I showed you a few things. I told you it was, I'm giving you guidelines. This is not a rule, it's a set of guidelines, which means that there's a lot of room for how you go about working with this thing, this set. And these guidelines are guidelines that I've written about in the text that you have and in previous textbooks, and not necessarily everybody in the world necessarily agrees that this is the way you have to do it. So if you're doing, but in this course, this is the way you sort of have to do it. You don't really have to do it. But when you get the midterm, the first midterm, there'll be some questions about modeling strategy on the midterm. And, you're going to have to sort of answer the questions in the way in which I've taught it. Because I'm saying, given the way I've taught about modeling strategy, how would you answer these questions in this, so if you have some other point of view, it's not going to work for this midterm. But it doesn't mean in general you can't have another point of view, okay? Does that make you laugh? I don't know what it makes you cry. I'm not sure what, So it's a three-stage strategy. The goal is to get a valid estimate of the exposure-to-disease relationship, and typically that means you want to get a point estimate, and if it's logistic regression, well, the main estimate, the main measure of effective interest for logistic regression, which you could use in different kinds of studies, whether it's either a cohort, a case control, or a cross-section study, the measure of effective primary interest is the odds ratio. Even though there are ways you can get an estimate of the risk ratio or the prevalence ratio if you're doing a case control study and you want to get risk or prevalence. But that's something that we're going to talk about later in the course after the midterm. It's actually going to be involved with this next midterm, but not this midterm. So anyhow, how do you deal with estimating something other than the odds ratio? And in any case, you want to get a point estimate of the measure of effect. You want to get a confidence interval around it to look at the precision. And you want to do a third thing. You want to do a test of hypothesis about whether it's significant or not. And then you also want to do, then I added on this thing, you also want to get some way of determining how important these results are, the clinical significance of it. That's not statistical. It's like, okay, you get an odds ratio that's 12 and it's very precise. What does that mean, given what you're trying to do? That's the clinical significance of it, given what you know about what you're studying. Okay, so those are the guidelines, and there's me way back a long time ago. There's Nathan Mantell, there's my buddy Larry, and we talked about the goal is primary etiology. The three stages involve variable specification, interaction assessment, and confounding assessment, followed by precision considerations. And what I said near the end of last time is that These are the 3 stages. There's different ways you can, you can work through these things, but this is the order in which you should do them, according to this strategy. You should do variable specification first, because that's where you're considering what you're working with and what makes sense in terms of the literature or the conceptualization of what you're studying, and that's why you should consider the variable specification step first. In fact, there's another thing you should consider at this step that I'm going to mention a little bit later when I get into it. You remember the course you had last semester meaning in the spring, from Dr. Howard's, right? What was the key thing in that course that you learned about? I know you loved it. You just loved it. You had so much fun with it, right? But she did it well. She does it well. What was the thing you learned about? DAGs, right? DAGs, okay. Right? I don't know if I said that right. So you learned about DAGs. Now, where does the DAGs come in? Where does that come in if you're talking about modeling strategy? Well, it comes in, first of all, even if you're not talking about modeling strategy, when you're designing a study, it has to do with, what you think should happen when you collect your data and analyze your data. But when you're designing your study and you're trying to figure out what your initial model looks like, which is the variable specification stage, that's where you want to consider the DAG, or a DAG, that allows you to decide whether certain variables should be in the model or not. In fact, you learned about, when you talk about DAGs, you've even learned about different kinds of DAGs. And I'll just, just to jump a little bit here, there's another PowerPoint presentation that talks about key DAGs. So I'm going to let's see if I can find it. Here it is. DAGs and modeling strategy. And what are DAGs? You know that. Key points about DAGs. Look at these 2 pictures. You've seen them before, and you've seen more complicated versions of this. Okay, and then there's a third graph. Okay, third graph describes a what's called, remember the word collider? Describes a collider. Well, that doesn't, that could happen, but I'm really kind of focusing on the first 2 graphs here. Okay, so if when you're starting to think about the variables that you're working with, and now I'm simplifying, and I'm only dealing with your exposure and your disease and one other variable. Usually you have several variables you want to control for. The control variables, I'm denoting as C's, even though when we talk about the EVW model, they go in the model as what? How do they go in the model? Control variables? In the EVW model, what are they called? V's. Very good. Okay, so here's a picture of a causal pathway, and what do you notice about the pathway? Is that the relationship between E and D goes through C. So C is an intervening variable in this pathway, okay? And what did you learn when Dr. Howard's talked about that? Okay, should you control for C if it's an intervening variable in your pathway? So if you decide that this when you're thinking about what you're doing, that you want to consider C as a possible control variable, and this is the way you think it makes most sense to write it. You don't want to control for C because it's an intervening variable. If you control for C, you might find there's no effect between the exposure and the disease relation, when in fact, this actually says there is an effect. It goes through C. Right? Now this picture is different. This is a picture where you've got what Dr. Howard's called a backdoor. I'm sure you loved all that. A backdoor path. Okay? But this is the picture that describes a situation where C is a confounder or a potential confounder, because the relationship between E and D comes from C. In other words, there may not be any relationship between E and D, but C goes to E and C goes to D, and it looks like, that's why it looks like there's maybe a relationship between the exposure and disease, but it's really because of C. Okay? Now, if you have this situation, then you want to control for C, right? So you learn, and that's where this comes into play. When you start to do the variable specification part of this modeling strategy, what you do is you may have to look at the DAG a little bit. I mean, you want to think more generally about the literature, what are the important variables you want to control for, but somewhere you want to have a DAG and use your DAG to make a decision about which variable should go in the model. If you got this thing, you don't want to put C in the model. You don't want to control for it. You understand what I'm saying here? Okay, and then, of course, it can get more complicated. Look at this. If you had this picture, this is the kind of thing that you started tearing your hair out, scratching your eyes, I'm not sure what, when kind of, this isn't that hard a picture, given everything else. What does this show? Well, I've got the words written over here at the bottom, but you notice that C1 goes to E, let's see. C1 goes to E and C1 goes to D, right? So it looks like C1 is confounder. What about C2 and C3? Same thing. This picture seems to show that these three variables you ought to consider, if that was your DAG, you want to consider controlling for all three, because it looks like they're each on their own confounder. Now, how that works when you try to put them all in the same model is something else. But you look at this DAG, it gives you an idea of how to proceed. Now, instead, if you had this, what does this say? What does this say? Well, did I say this right? Let me just see. What did I say? C goes to E. C1 goes to E, C1, okay. C2 goes to E, C2 goes to D. Okay, what about the next one? Okay, E goes to C1 goes to D, right? So in this picture, all three C's are intervening variables between the exposure and disease. If that was your DAG, you wouldn't necessarily want to control for either of those, any of those three C's. Got it? That's sort of the idea. That's where DAGs come in. And that's where you have to, if anything, they fit into this idea of the strategy. You want to think of it even before, but they fit into this issue. So that's all I'm going to say about DAGs, other than, it's important. It concerns us. So now I want to go back to where we were so let me see if I can find it. There we go. Okay. Okay. So there are these three stages. Okay. And I talked about, the order is you want to do variable specification first. You want to consider the DAGs in there in sort of deciding. We'll talk a little bit more about it. Interaction assessment comes second, because if you find interaction, then you want to make sure you control for the variables that affect modifiers, and you don't even want to consider, you have to control for those variables. You don't want to consider an effect modifier also as a confounder. It's a variable you have to control for. And once you deal with interaction, you want to consider confounding followed by precision. And confounding is sort of a more important point, because confounding deals with bias and precision deals with random error. So you want to make sure you got the right answer before you start trying to get a tight estimate around the wrong answer. That's what I said last time, I think. Okay, so now with all of this, and I also said interaction may not be an interest and all that. Now the last thing I said before we quit is that if you're going to assess confounding, we're going to talk about how to do this. You're going to assess confounding. You don't want to do a statistical test to assess confounding, because confounding has to do with the validity. It has to do with systematic error. So you don't do a statistical test. Somehow you have to decide whether or not you control for a variable, whether it makes a difference in the measure of effect that you're talking about. And you remember you learned about something called the 10% rule, whether that makes a difference, or you can just look at if you control for it and you don't control for it, you get an odds ratio of 4 versus 1. That would say, ooh, there's a difference. There's a meaningful difference between the two. You wouldn't even necessarily need a 10% rule. There's clearly a 10% difference if it was 4 versus 1. Okay? So, but that's a rule that helps you. So you don't test for confounding whether you're doing modeling or simpler analysis, like a stratified analysis, or even just stratified analysis, a simpler form when you're trying to control for one or more variables. So now, this is where I didn't get to, okay? So this is new, okay? Now, this is where I'm not really going to get to it much. I just want to mention a few things. There are some things you also have to worry about that we're eventually going to get to this to some extent in a few weeks, but not right now. 3 other statistical issues. One of them is called multicollinearity. Did you learn about this in Azar's course? A little bit? Okay, so we're going to talk about that again, but we're going to talk about it just before or just after the first midterm. It's not going to be on the first midterm, but I'm going to start talking about it because it's at that point where we're going to be talking about it. Okay, so and multicollinearity has to do with what I say here is that you've got a model and you've got these predictor variables in your model, which are often called independent variables, even though they're not necessarily really independent of one another, but you got these x's in the model. You want to predict the y, and it could be that some of the x's are very strongly, associated or predictive of some of the other x's. And if you got something like that in the model, it may turn out that the model either doesn't run, or you're getting a very unreliable estimate of whatever you're getting out of the model. Okay? The worst situation is, you already know about the worst situation. It's like you've got a categorical variable that you want to put in a model. It's got 3 categories. What would you do if you wanted to put that variable as in the model to look at the 3 categories? How would you do that? Dummy variables. How many dummy variables? 2. Why not 3? Because if you put a third one in, what's going to happen? The model won't run, because the third one's completely determined by the other 2. You built in collinearity. That's just a simple example of collinearity. But you can get collinearity even if you've got variables that aren't categorical and you're not sure, but they might predict others. So anyhow, that's an issue we have to worry about. We have to talk about that. Another issue is multiple testing. And one way to say that is, if you torture the data enough, it'll confess. You've heard that. Somebody must have said that somewhere, right? If you do enough tests, you'll find something. So one of the problems you have to worry about is, well, how do you deal with that? And I think you've heard in maybe Azar's course something called the Bonferroni correction. You heard about that? It's a way of trying to deal with, if you know that you're going to do 10 tests, and you're worried about maybe finding something by not considering the fact that you're doing so many tests, you're going to find something. You could take the significance level, the alpha, whatever the point, like if it's 0.05, divided by 10, and do the tests at 0.05 divided by 10. That's one way to deal with multiple testing. Problem when you're doing logistic regression modeling with trying to come up with the best model, you don't necessarily know in advance how many tests you're going to do. So how do you know how to adjust for it? That's sort of a problem. And it really is no really good answer, but Bonferroni correction is one thing, and we're going to talk about that to some extent. And then there's a third one called influential observations. Did you hear about that somewhere? What's an influential observation? It's a person. It's a person's set of data. It's not a regression coefficient. You may have 100 people or 1,000 people in your data set, and it may turn out that one of the people in your data set, one of the bits of information you have on that person, if you pull that person out of the data set, and then you run the model and you try to get an odds ratio, the odds ratio may completely change, may be very different. It may be very influenced by the individual or one or more individuals in your data set. So that's what's called an influential observation. So how do you detect that? And what do you do about it if you find it? Well, that's something we need to talk about, but that's later. Okay? So these are 3 issues. We don't have, we've got enough things to do today. So those are 3 issues. Okay? Moving on. Okay? Can I move on while I'm moving? Okay? Moving on. Okay, and I'm still looking at my time, saying to myself, I got a lot to cover here. But I want to do it so that you understand it. So if you don't understand it, you have to raise your hand. You could say, I don't understand what you're saying, and then I'll try to re-explain it. It's okay. You don't have to ask a very specific question if you want to. You could say, ugh. I do that pretty well, right? Okay, so now what I want to do is talk about the variable specification. How do you do that? Okay. Well, one thing you do is you look at your DAG, okay, and you decide what should go in the initial model. Now, variable specification is how do you get the initial model that you're going to work with? That's what I'm saying. Now, if you think about it, you do a literature review to decide what variables you want to measure in your study, right? And it's not only a literature looking at what people have done in terms of previous studies, it also has to do with the biological and clinical ramifications of what you're studying. So you don't just put the literature, even if it hasn't been studied before, you might want to consider biological or clinical issues and how you want to decide to put a variable in a model. You have to have a reason for telling that. You have to have a reason for all the variables you're considering. You have to reason for the disease variable, the health outcome variable, the exposure variable. You have to decide how you're going to measure any of the variables you put in. And you have to have a reason for the C's that you decide. And the reason typically is based on, it could be conceptualization, but it's based on the previous literature. These C's, or one of these C's, any one of more of them, were variables that were shown to be previous predictors or previously associated with determinants of the outcome. So you want to put it on your list. Why do you want to put it on your list? And you've heard this before. You want to put it on your list because if you don't control for them or take them into account somehow, and then you just run a whole analysis and summarize the results, and then you write it up and all that, somebody's going to read what you say, and they're going to say, well, you didn't take into account this variable. Why? Maybe this variable is explaining the whole thing. So you got to make sure you account for variables that might explain away the relationship that you're studying. That's why the C's are on the list. Okay, and a variable like that might explain it because of biological considerations. So that's the C's. So you're starting off with D, E, and the C's. Okay, and then what we said, you then want to sort of define an EVW model because that's allowing you to consider potential confounding and potential effect modification. And when you do that, the V's and the W's might be more complex than just the C's themselves. I mean, one of the C's might be age, and you might want to have, that means you certainly want to consider age in your model as one of the variables. But why not add age squared? That's not a C. It's a function of C. It's a mathematical function related. So it's a V. It's not really a C. And the same thing goes with the W terms, the product terms. So specify the V's. Now, how do you decide to do that? Do you do it mathematically? And I'm just giving a common sense answer to this, and that's what should make sense to most of you, but different people may have different ways to think what makes sense. So you could have a contentious group of people working together and you're arguing, having a fight. I don't know, not necessarily that. But I'm saying specific V's should be based on prior research or theory, possible statistical problems, one of which is collinearity, and really I should have added the DAG. The DAG that you think makes sense. That's how you choose the V's. Okay? And it's common sense, really, in terms of what, you've got to have that in there. And that's why it's first. You don't want to put in the color of somebody's eyes in there as a predictor if it doesn't have anything to do with the relationships that you're studying. Okay? So that's what I'm sort of saying here. And, well, multicollinearity could come in if you put in as many variables as you could possibly think of, even all the C's without even doing any complex functions of the C's. Well, you might be asking for some trouble because it may be some of the C's are predicting other C's. So you got to, worry about, well, you may find out if you know which you'll eventually learn, how to assess collinearity, to know what to do with that. So that's how you specify the C's and the V's. And the simplest thing is to make the V's the C's. Don't make it that much more complicated. If you want to control for age, race, and sex, make the V's just age, race, and sex. If you want to add age squared, age times race, age times race is a V, right? Why is it a V and not a EW term? Because it doesn't involve exposure if age and race are C's, right? So you can consider these other terms in addition to age squared. Now, of course, if race is binary and sex is binary, you square it, what do you get? Same thing. So that's why they're not in there. Is that a joke? I don't know. But anyhow, you can see this. These are the choices you have. And the simplest thing to do is to control for age, race. At least you're taking into account the variables that you've identified from the literature that you want to make sure you consider. Now, if you choose choice 2 or some other variation, this is not the only choice. I could have had age times race times sex, right? I could have had the three-way product term. Those are the only three. That's as far as I can get. Well, I could have age squared times race times sex. So I could go on almost forever. Age cubed, So where do you stop? Well, one thing, it's not clear where you stop, but one thing you should realize is that the more of these extra variables you add, the more you're setting yourself up for a problem where the model's not going to run or not going to run well. You know that? Well, you have to decide what's worth it to you to consider. When would you want to make sure you put in an age square? Well, if it turns out from previous studies of what you're looking at from similar health outcome and similar variables, age looked like it had a parabolic, not a linear relationship, but a curvilinear relationship, then you might want to consider age square. Now, of course, you could sort of look at the data a little bit and see if that makes sense too, and then put it in an age square. So you have some sense about what to do. But you don't automatically put in square terms for every variable you have in there. If I had 3 continuous variables, I don't automatically put in the squares of each of them. Okay? I could, but if I do, then I'm asking for trouble. Do I want trouble? I don't really want trouble. I want to get the right answer. You know, so, but there's always a trade-off here. So when you start thinking about how do you do modeling, you know, you're already saying, hey, wait a second, this isn't that easy. You know, if you think about what people do, and when you start thinking about what people write up in their papers when they say, well, we did this thing, and we did logistic regression, and we just somehow came up with the best model, what did they do? You know, and they might have not done so, and unless you know what they did, you know, key thing is, what do you do when it's your data? When you're doing your thesis and you're writing something, what do you do? There's still room for making decisions here. Okay, so now what about the W's? So I talked about the V's. Okay, what about the W's? Okay, the W's are those functions of the C's. They could be the C's themselves that go into the model as a product term with exposure. Now, by the way, I'm only talking about one exposure here. Things will get more complicated if I talk about more than one exposure, and that's for the next class. Talking about what if you have 2 exposures? More complicated, okay? But if you have 1 exposure, you know, what about the W's? Well, what I'm saying here is it's still not easy how you consider the W's. And to make it sort of reasonable, but to realize that you can't, you know, you can't have an exact rule of what you do. I say you should restrict the W's to be either the V's themselves or products of 2 V's, but not products of more than 2 V's. And there's a reason why I'm saying the V's and I'm not saying the C's. We'll talk about this in a minute or two, but what I'm saying here is if the C's are age, race, and sex, and you decide that the V's are age, race, and sex, then the simplest thing to do is to say the W's ought to be either age, race, and sex. That would mean that age, race, and sex go into the model as V's, and they also go into the model as a product term with times E. So you've got V's and W's, but you may not want to consider all product terms here. You may want to consider only 2 of them, or only 1 of them if what you would think that you got, whether they don't make sense, whether the product term wouldn't make sense even if you found it was significant or came out of the model. And that's not an easy decision to make. So you can throw in anything almost. Now this is where there's room for a lot of decisions and a lot of arguments about how to, I don't know, arguments or discussions of how you deal with it. So what I'm saying is the product terms shouldn't be more complicated than E, VI, VJ, because if they are, you're going to typically have collinearity problems, and you might have problems trying to figure out what they mean. If you have E times age times race times sex, and you find when you do the analysis that you have to keep that product term in there, what on earth does that mean? And if you can't figure out what it means, you shouldn't have put it in there in the first place, even if it's significant. I mean, you might want to figure out what it means, and if you can, that's great. Okay, so the simplest choice is just the simplest choice is not even to allow yourself to have EV, VI, VJ, just have EV. That way you're allowing for confounding involving the V's and interaction involving the V's. And if you have interaction, the V's that are in there as product terms are really W's. The reason for the W is because that's in there as a product term with E. Am I losing you, or are we okay with this? I mean, we haven't done anything fancy. I'm not doing any fancy mathematics here, but some of you are, I don't know, who knows? Okay, so where are we at this point? We have a flow diagram. We're starting with D, E, and the C's. And what we say is you then choose the V's from the C's according to what makes sense. And then you choose the W's from the C's, either as just the V's themselves or VI times VJ. And they go in the model as product terms with E. And that's if you have one E. It gets more complicated if you have more than one E. You with me? Not that. Now, you notice that regardless of how you make these decisions, you've already got to the point where regardless of what you decide goes in the model, you know how to fit the model. How do you fit the model if it's logistic regression? What are you going to use? If you're using SAS. Proclogistic. And if you fit the model and you want to test hypotheses about interaction terms, you know how to do that. You've already learned how to do that. If you want to fit the model and come up with an odds ratio given the model, you know how to do that. So what we're talking about now is how you work all this stuff together to come up with some answers that make sense. That's why this part of the course is sort of merging the epidemiology with the statistics, which you don't really get that much in your other courses up until now. Okay, so anyhow, now. There is a rule. There's one rule. It's not one rule. There's another variation of this rule. And the rule is, and Dr. R mentioned it last time when he was talking about matching. And the rule says, well, when you're deciding on your initial model, there's a rule about what variables you can put in the model, what variables you got to make sure are in the model. And this rule says the model has to be hierarchically well formulated. So you can, it's a term now you can name drop to all your friends, show how much you understand everything. Okay, was your model hierarchically well formulated? Going to just embarrass your friends or whatever in front of, was it HWF? Okay. So, and the rule says, and it's a simple rule: given any variable in the initial model, all lower order components of the variable must also be included in the model. That's what it says. Okay, so what does that mean? Well, here's an example. Here's a model. It's a logistic model, right? It's a logistic model. I've written it in terms of logit form. Okay, what's not in this model that should be in here? Well, if you look at the highest order term, E, V1, V2, well, E's in there, V1 is in there, V2 is in there, E, V1, and E, V2, but V1 times V2 isn't in there. Okay, so that model is not hierarchically well formulated. Now, I haven't said what's wrong with that. I'm just telling you what the rule is, right? So this model isn't hierarchically well formulated, and so because V1 times V2 isn't in the model, and if you put it in the model, then you have a model that's hierarchically well formulated. That's the next slide. Too quick? Did I do this too quick? I don't think so. But everybody's different. So, okay, what about this model? Hierarchically well formulated? You take any component in this model, and usually the way you do it is you look at the highest order terms, and you see if all lower order components of the highest order terms are in the model, the sort of subcomponents in the model, and that's true here. So this is a hierarchically well formulated model. This would be sort of legitimate, okay? So now the question is, okay, because both components of E times V, the EV terms are in the model. Okay, why require this? Why do you require this? Why do you have to do this? Well, the main thing, and Dr. R mentioned this, the main thing is if you don't have a hierarchically well-formulated model to start with, and you try to test hypotheses about some of the variables in the model, the tests there's something wrong with the tests. They don't work. You won't be able to determine the right answer, or you can get different answers depending upon how what different ways you put the model in. And I'll try to explain it, but what I say here is test, and I say test for the highest order variables. What's the highest order variable in this model? EV1, V2. Okay. Now, if you had this model and you were going to test for interaction, what test would you want to do first about interaction? For that one, right? That's the highest order term. That's the most complicated term. You might want to do I'm not sure if Dr. R used the term chunk test. What's a chunk test? You might want to test for whether delta 1, delta 2, and delta 3 are all equal to 0, or there's no product term should go in the model. That's a combined test. Okay, but it would probably make sense to test for this higher order term and then see what you get from that before you start considering the lower order terms. Okay, now what I'm saying is that if the model was not hierarchically well formulated and you wanted a test for this term, the test would depend upon the coding of the terms that describe this variable, the components of this variable. Whereas if the model was hierarchically well formulated, which this model isn't, then whatever test you do on this variable, on this coefficient, is going to be completely independent. Now, what do I mean by coding? Well, think of it. One of the variables, a key variable in this model, is E. Okay? Now, when you set up your data, you can code E as 0 or 1 if it's binary. And that's what most people do. But you might code it as 1 or 2. You might code it as 1 or minus 1. Right? There are a lot of different ways you can code it. Or 0 and 100. Okay? And what do you think I'm saying here? I'm saying depending upon whether you code it as 0, 1, 1 minus 1, 0, 100, you might get a different result for whether this variable is statistically significant in this model. Well, you don't want that. That shouldn't depend upon how you coded the variable. The variable is just, it's got 2 values. It shouldn't depend upon that. But if you have a model that's hierarchically well formulated, it's not, your answer isn't going to be the same. Now, just to give you an example of this, here's an example of this. Okay? Here's 2 strata. Okay? Now, if you look at these 2 strata, you notice that the odds ratio for this one is 36 and the odds ratio for this one is 1. Can you see that? Odds ratio AD divided by BC. This is 36 and this is 1. I think you can figure that out. Okay? So this says there's interaction, right? In terms of if the effect relating exposure to disease is very strong in this stratum and not at all in this stratum. Okay? Now, you've got this variable V, which is the variable that you're stratifying on. And the V could take, or even the E could take on different values. The V can take on different values, as can the E. Okay? Now, think about this. Here are 2 models that I could use to fit this data. Here's one, and here's the other. And one of them's hierarchically well formulated, and the other isn't. You see that? First one's hierarchically well formulated because the highest order term is EV1. V1 is in the model, and E is in the model. But this one isn't, right? Because it's got the product term without the lower order components, right? Big deal, okay? And so what, and then suppose I have different ways I could code any of these variables, and if I want to code my choices of these variables, I could code 0, 1, minus 1, 1, 1, 2 for either E or V. Okay, what would happen if I changed that? Well, look at the results here. Look at the results. I've got these 2 models. Now, this may bother you to try to see all this thing on a screen. How do you make any sense out of it? But let's just look at it here. Here's the model that's hierarchically well formulated. Here's the model that's not hierarchically well formulated. Now look over here. You see the 32.4420? What's that doing? What's that? That's the Wald chi-square for the significance of that product term, right? Okay. What do you notice about whether you code it this way, 0, 1, minus 1, or 1 and 2? What do you notice the result is? It's identical. You get the same conclusion, and it's identical regardless of how you've coded E in a model that's hierarchically well formulated. Okay. Here's the model that's not hierarchically well formulated. What happens? Well, these tests are different. I mean, all 3 of them reject. You know, this is just an example, but it could happen that some of them reject and some of them don't reject, depending upon your data. So what this says, if the model is not hierarchically well formulated, how do you, and you have to worry about how you coded the variable, and you don't know what the right, you know, you can get different answers depending on your code. 0, 1 isn't necessarily right, and you're going to get different answers, but you don't have to worry about it here. That's why it's required. Okay, that's why you have to have it in there. If you don't, you can't depend upon these tests for, now it's for the higher order terms. There is an issue about the lower order terms. We'll talk about this now. Now, in any case, where we've gotten here at this point is we're starting with an initial model that we've decided based on the variable specification stage has E, V's, and EW's in the model. That's our starting point. And then eventually we're going to wind up with a final model, the end of the whole story, which we're going to make decisions about the exposure-disease relationship testing and confidence interval and so on. So what do? We start with the initial model, and if the initial model has terms as complicated as E, V, I, V, J terms, those are the terms we want to consider first to eliminate, because they're the highest order terms, they're the most complicated interactions. Okay? Once we do that, the next thing we do, now you could have had E, V, I, V, J, V, K terms. There's nothing to say you couldn't do that. And there'd be another box that you'd have to put in there. But you're asking for trouble. You can give yourself the trouble if you want to, depending on what you want to do. Okay? But this is what you do, in as simple way as possible, and you might not even want to consider these terms. You might want to just start with the EVI terms. And now you notice I say testing, testing, but for this part, I say no testing. Why? Why? Because these terms have to do with what? Interaction, of whether there's an interaction between exposure and a variable you control. This has to do with confounding. Even with regard to, see, the VI, VJ product term, it's not an effect modifier, it's a product term. It reflects interaction of one V with another, but it doesn't reflect interaction with E. So that has to be considered as a potential confounder. And you don't test for this. If you want to consider these, you have to do something else. You have to consider whether an odds ratio changes. So that's where we are at this point, okay? Now, we're not done because it's early. Okay, now here's another thing. Here's another thing. By the way, are we having a good time? I don't know. I am. I'm having a lot of fun. Okay, so here's another thing. So we're starting with this model. Okay, now, and we're going through this process like I just described here. Okay, now suppose what happens is when we go through this process, we have a term like EVI, VJ. We have a bunch of terms like that. And suppose it turns out that maybe there's 5 V's or something like that. Maybe there's a lot of V's. And it turns out the only, or it could be more than one, but let's say the only EVI, VJ term, we've decided to allow them in the model, that's significant is EV2, V5. Okay. Suppose we find out when we start this process and we're looking at interaction, this thing comes out to be significant, this term, its coefficient. So what does that mean? That means we have to worry about the interaction of E with this product term, whatever interpretation we can give to that. Okay? But what does it mean about the rest of the modeling process? This is where we're talking about model building. What about the rest of the model process? Well, it means that, what I said, if this is the case, then we have to keep the variables that I've listed in the rest of, we can't drop any of the variables I've listed here. E, V2, V5, E, V2, E, V5, and V2 times V4. We can't even test for any of these other variables to try to see if we can drop them. That's what I've said. Why? Well, I have the answer here. The initial model must have V2 times V5 to be hierarchically well formed. But suppose we test for them. Suppose we leave this in the model, and we test for V2 with this in the model. Okay? We test for V2 with this in the model. Okay? And it's significant or not significant. And let's say it's not significant. We decide to drop V2 from the model. We drop V2 from the model. Then what model do we have left? Is it hierarchically well formulated or not? It's not. So we're messed up. So that's why when you start with the highest order terms, if you find you have to keep some of them, all the lower order terms have to be kept in. Now, that doesn't say, if it's V1 through V5, that doesn't say that you have to keep in V1, V3, or V4, right? It just means you have to keep V2, V5, EV2, and EV5 in the model, but you can drop EV1 if you figure out how to do it, okay? So, that's why we're talking about this, because there's issues here that try to, But I think you follow what I'm saying, because we're not talking, this is not higher mathematics, it's just conceptual thinking, okay? But we got to do that. And this idea that it's called the hierarchy principle. And it says it's sort of related, it's clearly related to the hierarchically well formula, HWF. It says if a product variable is to be retained, then all lower order components of this variable must also be retained. That's what it says. So that's another sort of a rule. But it relates to HWF. As you're going through the process, you have to keep the model HWF. If you drop something, then you're back in, Never Land or something. Shouldn't be doing that. Okay? Questions? Are you awake? Okay, so let's look at an example. The MRSA, let's look at the example, and then I'm going to walk through this example. Okay? Well, here's the MRSA example. You've already gone through it. The outcome is MRSA, yes or no. One exposure variable, at least the way we talked about it, previous hospitalization, yes or no. That's the one of interest. Is that related to whether somebody has got, is resistant to Staph aureus, being treated for Staph aureus infection? And you got three variables you want to control for, age, gender, and PAMU. So we have to start off with an initial model. That's what we have to do. Okay, and we have to look at our DAG, or one way to do it is we decide on what the DAG is, and or we just decide to come up with an initial model. Now, I have to start somewhere, in order to do this. So I'm going to assume that whatever DAG that makes sense allows me to make this as my initial model. I just clicked, I got to the next slide. What have I done? What have I done here? Can you see what I've done? Now, I'm using V1, V2, and V3, but V1, V2, and V3 are the three variables, the three C's, right? And W1, W2, and W3 are also the three C's. So what I'm doing is I'm doing the simplest possible thing I could do, is I'm controlling for the confounding of the three C's, and I'm allowing for the three C's to be possible effect modifiers. That's my starting model. I could make it more complicated. I got to start somewhere. This is complicated enough, okay? Gets more complicated. You might get a question, it's more complicated on the midterm. We've got to make sure we do this, know how to do this. Does that scare you? Did I scare you? Ooh, midterm. Got to be careful not to say that too much. Okay? But midterm, our goal there is not to kill you, make you feel horrible. It's just to give you a chance to show us what you know or demonstrate to us that you've learned some stuff. Okay, so now, is this model hierarchically well formulated? The answer is yes, because we've already seen it. It doesn't look like it is because you've got W1, but W1 is the same thing as V1. So if EW1, the lower order terms of that are E and age. So they're in the model. So this model is hierarchically well formulated. Okay, first step is done. What about interaction? How do we do that? What do we do? Now, you know how to test for interaction. You know how to deal with interaction. Well, the simplest thing you might do, and I'm just going on here, the simplest thing you might do is say, well, look, I got these three product terms in the model. Let's do a, quote, chunk test for whether they're significant taken together, right? How do you do that? You know how to do that. We've reviewed this in the first week or so, and you had it last semester. How do you do it? Chunk test. What's it called? Likelihood ratio test. What's the null hypothesis? In terms of the model, what's the null hypothesis? Well, one null hypothesis is none of these three things are significant. Another way, in terms of the parameters, is that delta 1, delta 2, and delta 3 are all equal to 0, right? Because under that null hypothesis, the model reduces to the no interaction model. So you do a likelihood ratio test, okay? How do you do that test? You have to fit two models. The model you see and the reduced model. And what's the reduced model? The no interaction model, okay? And you look at -2 log maximized likelihood that comes out in the output, and you get them from both models, you subtract one from the other, and that's your chi-square statistic, right? You know how to do that, okay? And then you have to determine the degrees of freedom. What is it? 3, because you're testing whether you're setting 3 parameters equal to 0. So that's how you do it, okay? So suppose you do that. Now, it turns out, let's talk about what would happen if you do that and your result is statistically significant. Suppose you do it and the result is statistically significant. What would you do next? What did you, this is, let's see, I'm trying to say, Avnika? Farah? Sobia, okay. Well, third time's the charm. Okay, so what you would say is, well, do you need all three in? That's what you're saying. You know, I've done this chunk test. It looks like I need to have at least one, maybe all three in the model, but can I get rid of some, right? How do you do that? How do you do that? Well, you learned last semester in the regression course. Backward elimination. Okay, but it's not the standard backward elimination because not every variable is competing to be dropped out. You're going to make sure you keep E, V1, V2, and V3 in there. You're only talking about backward elimination about these three product terms. You're not allowing yourself to drop any one of these other. They stay in the model because you're at the interaction stage. That's why this is different than the standard backward elimination, which lets everything compete. Get what I'm saying? Okay. Well, anyhow, okay, so you do backward elimination. So what happens if you do backward elimination and you get rid of two of these, but the third one stays in? By the way, how do you do backward elimination? You do it one at a time. You try to drop the least significant of these product terms, and then if it's not significant, you refit the model with what's left. If it is significant, if the least significant one of the three is significant, what do? You can't drop anything because everything's significant given the others in the model. I mean, supposedly you learn that, but you may have to think about that. So that's, you know, and then if you find that the least significant one is not significant and you drop it and then you have two left and then you ask the same question of the ones of the two left, which one is least significant? If the least significant one is not significant, I should drop that. But if it is significant, I can't drop anymore. That's backward elimination. Okay. Now it may happen that you drop one or more, you can't drop any. Okay. So that's sort of how you would sort of proceed if it was significant. What if it wasn't significant? What if and it turns out for this particular data set, it's not significant? What if you do the chunk test and it's not significant? What are you tempted to do? Drop them all. Okay, right? You're tempted to say, well, look, there's no interaction. I'm done with interaction. I'm going to get down to confounding and I'm not going to worry about it. What's a potential problem with that? What's a potential problem with that? Well, let's assume there's no collinearity. We're not even worried about collinearity. The model's okay. But what's a different potential problem? Let's say that's not a problem. Okay? The problem is it may turn out that even though the chunk test is not significant, if you did backward elimination, it could be one or two of the variables are significant once you drop one of them or two of them. Could be that the reason why the chunk test was not significant was because you had three variables in there and they're blocking each other out. And it may be that one variable is really significant, and if you drop everything, you're never going to find that unless you do backward elimination. You get what I'm saying? Okay, so that's going to make you think, oh, well then, why are we even doing why are we doing the chunk test if we're going to do backward elimination anyhow? Okay, well, we'll talk about that. Okay, but let's see what happens with these data. Okay, so what I'm saying is carry out a chunk test, and this is a flow diagram of what I just said, and I'm going to skip that. I'm going to talk about how do you test whether there's no interaction of any kind in the model. I've already talked about that. Okay, and I said you do a likelihood ratio test, and it turns out the likelihood ratio statistic with 3 degrees of freedom is not significant. Okay, so here you got a situation where it's not significant, and you might be tempted to drop all three. Okay, now I'm saying, well, wait a second, maybe I ought to do backward elimination to see if something stands out once I've dropped some of the others. Well, so I said if above this is significant, what you do next, we already know that you would do backward elimination. And if the above is not significant, what would you do next? I've also said backward elimination. Okay, so let's see what happens. Here's the first step. backward elimination. Okay. Now, you noticed I said drop PRH age. That's the product of previous hospitalization and age. Why did I say that? And I'm doing just wall tests to do this. Now, technically speaking, I really want to do likelihood ratio tests because the wall test and the likelihood ratio test might give different answers. So if this data was really important to me, I wouldn't do the test using a wall test. I would make sure I did the likelihood ratio test, which is a little bit more of a problem because in order to test for whether any one of these variables, I'd have to run 2 models. With a wall test, I only need to run 1 model. You know what I'm saying? Okay, so, but if I run this one model, and then I can see, why did I say drop this? Because this is the highest p-value, right? It's the highest p-value, and it's not significant. So that would be the first one I drop. That's how you do, you know. Now, you notice that I wouldn't say, well, all 3 are not significant. I'm going to drop all 3. That's wrong. That's not backward elimination. Because it's doing, each one of these things are p-values for one variable given the others in the model. It's not a chunk test. It's not equivalent to a chunk test. So don't make that mistake. Some people do it, make that mistake. Okay, here's the next step. I've now got rid of PRH age, and I've got these 2 left. Well, I've got 2 left. That's step 2. And you notice this is the highest p-value, and it's not significant, so I drop this one, right? Drop this one. You agree with me? I'm doing the wall test. Okay. Now, here's the 3rd one. I've dropped it. There's only 1 left. And then I got the p-value for that one product term, and it's 0.2122. Also very highly non-significant. So what do I conclude when I do backward elimination? I don't need any of them, right? And it's the same conclusion I got from the chunk test. Will that always be the same? Will it always be the same that the chunk test and backward elimination will give you exactly the same conclusion? Not necessarily. I wouldn't have asked that if it was true. Not necessarily. Now, for example, suppose you did all this and instead of getting 0.2122, you got 0.001 instead of 0.2122. Suppose you did that. Suppose that's what happened. What would you do at that point? Would you get rid of all 3 product terms, or would you make sure that this one, this last one, stayed in? Wouldn't you keep the last one in there? Okay? Because when you get rid of 2 of them, one's significant, it didn't show up when you did the chunk test. Okay? That's possible. You can get different answers from the chunk test and backward elimination. Now, does that answer the question, why would you do the chunk test at all? Why do the chunk test at all? It still doesn't quite answer it. Okay. Now, for example, if it turns out, but if you got what I just described, clearly you'd want to go with the interaction thing. I mean, with the, you want to keep this variable in there. But what if instead of 0.2122, and I said what did I say, 0.001 or 0.00 some, what if it was 0.0049? What if this was 0.0049? Okay. Is that significant? Well, it depends. It's significant at the 5% level if you want to use 5%, right? It's not significant at the 1%. It's sort of like what some people call borderline significant. Okay, so here's what would happen is if you did backward elimination, one of these things looks like it's significant, and the other 2 drops out, but it's hardly significant. So I go with the chunk test. So that's what I'm saying. That's why you want to do the chunk test. Anyhow. You want to do them both, and you want to consider what you would get if it was 0.049. I'd probably go with the chunk test and drop all 3. This isn't much. I'm not getting a lot of significance for doing. Or, you know, I might have an argument with my fellow researchers and say, well, I got to keep this in because it's significant. You know, but you could go with the chunk test in this case. And this is the kind of decision people have arguments about, you know. So, anyhow, okay, so at this point, we've taken care of interaction. For this model, there's no interaction, right? So we're now left with this no interaction model, right? That's what we're left with. Okay, so what do we do next? What do we want to do? Well, what we want to do is we want to say, well, is this our final model? And the answer is, well, if we want it to be, fine, but if we want to worry about something, it may be, maybe we don't need a control for these three variables, even though we identified them from the literature as variables that are important to consider, but we might want to drop them because one or more of them might not be a confounder, given the others in the model, okay? That's one thing. Now, if we let's say we decided that we could drop gender, which it turns out makes sense, actually, for this data. Suppose we decide we can drop gender, okay? And if we drop gender, we determine that it's not a confounder, okay? Okay, well, what's good about that? Well, we've got a simpler model. We haven't controlled for a variable we don't really have to control for. What might we worry about, however, if we decide to drop gender because it's not a confounder? What might we worry about? Okay, in terms of the two models, the model we started off with, which is sometimes called the gold standard model, I refer to it as the model that has everything in it, with the model that drops gender. What might be the case for the gold standard model that's different from what, think about it. Both models are trying to get at the exposure-disease relationship. What's the formula for the exposure-disease relationship in this model, the gold standard model? What's the formula? E to the beta. If I drop gender, what's the formula for the odds ratio? It's also e to the beta, but the beta may change. That's where you're talking about confounding. The beta, if the beta changes and e to the beta changes by more than 10%, then you got a confounding thing. Then you got confounding. Okay, so that's what you're trying to do. But it may turn out that even if e to the beta doesn't change by more than 10%, so you don't need to have gender in the model for confounding. It may be when it's in the model, you actually gain precision by having it in the model. So that's the other thing you want to worry about precision. It may be, even though gender is not a confounder, if you put it in the model, you may gain precision by keeping it in the model that you're not seeing by just automatically dropping it as from a non. So the reason why you want to consider dropping non-confounders is because it's, number one, it's a simpler model, and you don't need a variable to control for to get the right answer, but it may be you lose precision. So you want to consider the possibility of considering a model that keeps the variable that you might think drop. Is this getting confusing? I don't know. But anyhow, let's see what happens. So confounding assessment, the way you do confounding assessment, you drop one or more of the variables, age, gender, and PAM, to see whether odds ratio estimate for the effect of E changes meaningfully. That's what you do. Okay? So let's do it. Well, first of all, here's the model, and here's the output for the model. And so these are the three variables in there. Can you see this slide? Can you see this slide? I don't know if you can see it in the back, but anyhow, you could see it if you have your computer here. But anyhow, here are and here's the odds ratio estimates. And you see 4.417, what's that? What is that? That's the odds ratio. That's e to the beta, and what's the beta? 1.4855. That's the coefficient of the exposure variable, and that's the odds ratio for the effective exposure when you control for all three variables, right? That's what you get. Okay, and you can see the confidence interval around this odds ratio. You know how to get confidence intervals, but this is what it would turn out to be, and it's fairly wide. I mean, it's not real narrow here. It's just somewhat loss of precision, or not a lot of precision in here, but that's the confidence interval. Now, so what if you wanted to worry about, well, can I drop one of these three variables and see if the odds ratio changes? And I want to consider the 10% rule. Okay? Now look at the next slide. Look at the bottom of the slide. So the model that we started off with, again, is the gold standard model. And that odds ratio was 4.417. That's what I got from here. And I just wrote it again over here, 4.417. So what if I wanted to use the 10% rule? Okay, what I'd want to say is, what's 10% of this value, 4.417? That's the odds ratio. Well, what I do is I have the gold standard plus or minus 10% of the gold standard, and I get a range of values, 3.975 to 4.859. What I'd have to do is I'd take 10% of 4.417 is 0.44. So I'd add that to 0.442, and I get 4.859, and I'd have to subtract something to get the lower bound. Okay, now look at what I've done on this slide. I've dropped age. Do you see age in this model? It's not in this model. I've dropped age. Okay? Now, when I drop age and I look at the coefficient of the exposure variable, it's 5.274. Why do I put an X over here? Why did I put an X over here? Because it's not within this interval. If I drop age, I get an odds ratio that's more than 10% from the gold standard. See what I'm saying? If I wanted to use 15%, it might be within, so there is an issue about what percent do you use. But if I decide it's 10%, that's what I'm getting. I'm getting, it says I can't drop age if I want to use the 10% rule. What about this one? What about this one? 4.340 is in there. So I can drop gender, right? That's what I've shown you. And now what I've done in the next several slides is, okay, I drop PAMU. And then I drop age and gender. I'm doing this fast. And then I drop gender and PAMU. And then I drop age and PAMU. I consider all of this. And then I take everything I've done and I put it in this table. Put it in this table. This is a summary of everything I've done. So what is this table doing? It's considering all possible subsets of the three variables that I'm worried about controlling for. I mean, one subset is just put them all in. Another subset is leave them all out. Another subset is control for one of them, whichever one it is, or consider it the three. Another one is drop one of them, but keep the other two in. So these are all possible subsets. See what I've done? I'm just summarizing in the table. Can you follow this? It's what I've done. Okay. Now, and these are the odds ratios. You remember 4.417? That's the gold standard one. This is the one for dropping gender. V's in the model doesn't have gender. And every other one is not within the range, the 10% interval. So there's only one model that I could use as a competitor to the gold standard model. See what I've done? There's only one model. And this might, if I had a different data set, I might get more than one model. But there's only one model because it makes it easier to talk about and think about. It's only one model. So I now have, now you notice it says less than or equal to 10%. There's only one yes here for this model, right? So then what did I do? I said, well, look, we know we don't have to control for gender. And we get the right answer, so to speak, within 10%. But what about precision? What about precision? Well, what I do is I get the 95% confidence interval for the odds ratio, e to the beta, for all these different situations. But you notice I only put two confidence intervals up here, this one and this one. Why didn't I put the other ones? Why is there only two sets of confidence intervals in here that are in bold and the other ones aren't in bold? Huh? I didn't hear you. Well, because these are the only two models that are comparable now. You can't use any of these other models because they don't control for confounding. There's only one model that controls for confounding and drops a variable. So if I want to consider precision, the only two models I can compare are these two. Okay? Now, how do I consider precision? Well, again, precision could be looked at two ways. One way is, well, what's the width of the confidence interval? What's the highest minus the lowest? Okay? And when I do that, I get 7.730, 9.734 minus 2.04, 7.730. When I do this, I get 7.470. So which one is more precise? The one that drops gender, right? Because its number is smaller. Now, what's this thing? This is called the confidence interval ratio. Okay, this takes the 9.734, divides it by the 2.04. And this takes the 9.461, divides it by the 1.991. This gives you two numbers. You notice which one, if I'm using this measure, which one is more precise? This one is smaller. Whichever one is smaller is more precise. Now, people tend to use the ratio when you're dealing with logistic regression because you've got this upper and lower bound, and if you want to make sure that, I mean, suppose this was, instead of 2, suppose this was 5. I mean, you want to consider where the lower part of the confidence interval starts. That's a reason why people tend to want to use the confidence interval ratio. You could use either one, but For models that are nonlinear models, like the logistic regression, for linear model, you typically want to use width. For a nonlinear model, you want to use ratio. I'm not going to say much more than that, but we can talk about it in the lab next time. But that's what you want to. So it looks like no matter which model you use, no matter which of these two models you use, there's only two models that are eligible to be compared. And of the two models, the one that drops gender controls for confounding and gains precision. Right? So is that the best model? Well, if you're following the strategy, that says it's the best model, but you're not done, because what's the odds ratio? If you decide this is the best model, what's the odds ratio? That's the odds ratio. Is it significant? Well, you can look at the confidence interval to decide whether it's significant, and it is significant. And you can look at the confidence interval to see how, or the CI ratio, particularly the width, to see how much, or it doesn't have a lot of precision. So that would be your conclusion. Now, there's a problem with making the conclusion that gender is the best model. What's the problem? And this is a problem you always get when you're dealing with this. The problem is, okay, you gain precision when you drop gender, and you don't need to control gender to deal with confounding. Okay, you gain precision. Okay. However, do you gain a lot of precision? You don't gain a lot. What's a lot? I don't know what a lot is. You're going to have to make a judgment about that. But if you decide that it's a lot that you gain when you control for gender, when you drop gender, then you leave gender out. So there's an issue that you always have to run into when you're dealing with that. If you gain precision by dropping a confounder, how much precision do you gain? And this is a judgment call. That's why Nathan Mantell said, modeling strategy is an art. The more you get used to this, the more you might be able to make decisions about it, but it's not that easy. So we just did this now. This was a no interaction model. Okay? I just went through the process. This was what I call the all possible subsets way of dealing with confounding and precision, coming up with the best model using these three stages. We just went through it. Okay, that's what we did. Yeah, this is, what is it? Nicole. Okay, Nicole. Parsimony is another issue. It's true. If you drop gender, you got a simpler model. So again, there's a trade-off. There's always a trade-off. If you drop gender, you got a simpler model, doesn't control, you don't need it to control for confounding, but you lose a little precision. Is that worth the fact that you didn't gain that much precision by dropping it? Who knows? That's what, all of you folks on the research team have to talk about. There's no easy answer for this. And if you don't like the fact that there are no easy answers for this, I don't know, do something else for a living. I'm not sure, but that's the way it is when you start to, or don't worry about model strategy. If you don't worry about model strategy, though, then I don't know. Okay, okay, now here's what I want to talk about next. I'm skipping to a bunch of things because I want to talk about, well, what if there was interaction? And I don't have a lot of time to do it, but I want to start talking about it because I want to get somewhere with it. Okay, so can you find this slide? I'm skipping. This is what I often have to do if I want to get to something that's I think is more important than the other stuff in there. Just sort of summarizes some things about what do you do about confounding and all possible subsets and all of that. But what if there's interaction? What if there's interaction? How do you deal with confounding if there's interaction? Now look at this model in the middle of this slide. Look at this model in the middle of this slide. What does this model do? Is there interaction in this model? Okay. Now, the data didn't give that. This is not appropriate given the data, okay, that we had. But suppose I had different data. And suppose the different data, when I checked for interaction and did backwards elimination, I found that I had to keep this product term in the model. That's what I'm saying. Suppose I had to keep the product term in the model. What do I do about confounding here? Well, first of all, what variables are eligible to be dropped from the model as potential non-confounders? Gender and PAMU. right? But not age, because age is in there, has to stay in, because that hierarchy principle, right? Okay, so can't drop, well, I wrote it here, can't drop age. You can see that, okay? So how do you deal with confounding? So what's the odds ratio formula for this model? If you want to get an odds ratio for the effective exposure, what's the formula? Well, you know how to do that. It's what? It's e to the beta plus what? Plus delta 1 times age. That's the formula. Next slide. There it is. There's the formula for it. Okay? That's the odds ratio. So you're asked, and if you're trying to talk about confounding, what you're saying is, does this odds ratio change depending upon the values of these other variables that are in the model? Gender and PAMU. These are the variables that are left. I can't worry about age, has to stay in the model. Do these change? Well, the problem here is that I have age in this formula. So I'm not getting a single, e to the beta when there was no interaction. I just had one odds ratio, e to the beta. But now, do I have just one odds ratio that I have to worry about? Well, the odds ratio is different depending upon what age is, right? If age is 30, I plug 30 in here and I have beta hat and delta 1 hat, I get a different number, different formula than if age is 40 or 50. So I'm getting different values for the odds ratio depending upon what the effect modifier is. That's what effect modification means. The effect of exposure differs depending on the effect modifier. That's what this means, okay? So the problem is I'm not getting a single odds ratio because I get a bunch of them. So how do I assess confounding? Well, the answer is I must consider tables of odds ratios. Okay, what do I mean by that? Well, look at the bottom. Next slide. The bottom of the slide. Okay, what did I do here in the bottom of the slide? There's the formula, and now I've written several odds ratios, OR1, OR2, OR3, OR4, and OR5. What have I done? I've chosen 5 different values of age. Now, it's up to me to choose what values of age I want to choose. It could be that I could divide age into quintiles and choose the mean value of the quintiles and make sure the age is where the data is. But I've chosen different values of age, and I've computed these odds ratios for the different values of age. Now, what I've done is I'm going to get a table like this for the gold standard model. I'm going to get a table like this if I drop either gender or PAMU. I can drop them. I can't drop age. I'm going to get another table like this. So what am I asking? I'm not asking whether the odds ratio changes. I'm asking whether the table of odds ratio changes. That's what I'm saying. It's more complicated and it's more subjective. So here's some examples of that. This is where we're about to quit, but I want to make sure I show you this. Okay? So here, and this is made up results, just to show you, because this wasn't in the model. But suppose when I controlled for gender and PAMU, when I left them in the model, then it's my gold standard model, because I have age and I have their product term. Suppose I chose 5 different values of age, and these were the odds ratios. Suppose if I dropped V3, which is PAMU, these were the odds ratios. Suppose if I drop V2, I leave V3 in there, these were the odds. Suppose if I drop both, these were the odds ratios. What do you do with this? What do you do? What I'm asking is does the table of odds ratios meaningfully change when I drop one or more of the variables that I can drop? And the only 2 that I can drop are gender and PAMU. I drop them one or both, or leave them together, leave them in. Now, look at these 2 tables, the first 2, this one, the 5.2 for the gold standard. What do you see about this? Does the odds ratio collectively change when you drop V2, you drop V3? Does the odds ratio collectively change? Well, it changes to some extent. Does it change a lot? No. So it looks like if I drop V3, the odds ratio is not going to change very much. So it looks like I can drop V3. What about here? If I drop V2? Well, look at this 5.2, 9.2. That's a big change. Okay. Now, it's not true for the second one. big true for the third one. So it looks like and this is a judgment call, but it looks like if you look at dropping V2 and keeping V3 in there, you don't want to use that model. Because the table of odds ratios changes a lot. Part of the table changes a lot. Whereas when you drop V2 and you leave V3 in there, it doesn't change much. And if you leave out both V2 and V3, it changes a lot. So of the different models you have to choose to compare with the gold standard, this is the only one that's competitive with it. So now you're saying, well, look, based on looking at confounding, I can drop V3 and leave V2 in there, and the odds ratio doesn't change. So now I've gotten down to the point I've got two models. I've looked at confounding, and I've got two models. Okay, what do I do next? What do you do next? This is sort of the last line in today, and I'll start with it next time. What do you do next? Well, what did we do before when we were dealing with just, we had no interaction? What we did was, once we decided on confounding, we then looked at precision to see what we could do next in terms of whether we gain precision. Well, look what I show you on the next slide. Well, we now consider confidence intervals for the different choices of the ages. And I only have two choices now. I have the gold standard model and the model that keeps gender in there and drops PAMU. Look at these three things. Now, look at the confidence intervals. Do you gain precision when you drop PAMU? You gain precision. You gain precision. Look at it. I'm looking at these, and these are the CI ratios, confidence interval ratios. Do you gain precision? Well, you don't gain it here. You lose a little bit over here. But if you think about what happens for the entire collection, you gain precision. So if I had to choose between the two models, I would drop PAMU. I would be controlling for confounding, and I drop PAMU because I control for confounding, and that's what you do with interaction. It's more complicated. And some people say, if you've got interaction, it's so complicated that I'm just not going to worry about confounding. I'm just going to control for everything, because it's too subjective to make these decisions about tables of odds ratios. Now, on the midterm, I'm going to force you to make some kind of decision, some kind, I think. But anyhow, that's the story. So we've talked about modeling strategy for a single exposure variable. Okay? Next time we're going to talk about what if you've got two. And there's some other things we'll talk about. Do you follow this? Was this the worst thing you've ever heard in your whole life? Raise your... No, I don't want to know the answer to that. This is Tess. No, it's not Tess.
I'm Beryl.
You're Beryl?
Yeah. I've never spoken class before, but...
Beryl. Okay.
I had a question about...
Okay. Let me get rid of this. Let me just get rid of this. Get my this up before you start. Stop this.